Hello and welcome to lecture six, talking about encapsulation. What do I mean by that? Well, as you've seen from the last lecture, we're off and running, right? We originally, over the first four lectures, we were able to build anything you can do in structural Verilog. We can build designs, great. But then we started actually using the power of programming with Scala to actually construct generators, right? So in the last lecture, we've talked about using things like for loops, vex, seeks, etc., to actually build parameterized generators that have some non-trivial actual generation and parameterizability. And so we keep adding stuff in. And so to keep adding stuff in, we're going to want to, of course, have some structure, right? Some way of like having hierarchy, some way of having things encapsulated. So encapsulating, of course, the goal is to um, hide details intentionally so that we don't have to worry about certain things, right? So what does that mean in practice for today? We'll be talking about a little bit more Scala, kind of the same as we have all quarter, right? A little bit of Scala, a little bit of chisel, and then some design application, right? So we'll talk about some more Scala things, use that to build up some chisel components and actually demonstrate some additional chisel use cases for them. Cool, let's go ahead and see that. So fire up a notebook, sure. Get the headers in there. Alrighty. So we've made it all the way to lecture six, and we never told you how to write a function in Scala, right? So yeah, let's fix that, right? So they call it a method, right? And there's a few different syntaxes, and there's some nuances, right? So for a function by itself, yes, you just say, hey, def function name, argument list, and you can directly say equals and then give it the body, right? So if I want to find a function plus one that, takes an argument and adds one to it, yeah, great. And remember also in Scala, we have this interesting syntax of the type, if you want to give a type, goes after the name, right? So name colon type rather than, int n, it's n colon int, right? But okay. So yeah, you can see how this gets evaluated. We define the function plus one, sure. Here I call that function like you see in other languages. You give it an argument, gives you the answer, six. Now, um, this is a full-fledged language with a lot of things being first class. So what can I do? I can make a function that will do plus x, right? In other words, rather than always being plus one, it'll be n plus x. And notice how, sure, I can write that easily. Uh, So of course, 5 plus 2 is 7. What's interesting is I gave x a default value, right? So if I don't specify x when I call it, it's going to be x is going to get a default value of 1. So that's why we get 5 without x specified, default value of 1, then we get 6. Cool. So these are just some examples, kind of warming up. These are trivial functions, right? They're one-liners. And when they really are one line, writing it like that is the most clean way to write it. Of course, larger functions uh, can have braces around them. Now, when you have a multi-line function, the return value is going to be the last line that's executed. Uh, cool. By default, I can't change the arguments. Looks like we saw with the classes. If you want to make it changeable, of course, you can label as a var inside the argument list. I don't recommend that, etc. And usually these functions aren't freestanding. Usually they're inside of some sort of class or object. Um, cool. This is like the very first set of Scala methods. Any questions? A lot of like you see in other languages, right? I think the most atypical things are the fact you use equal signs rather than braces to kind of demark the start of the function, and you have the types go second. Yes, good question. So I want to return more to one thing. How do I do that? Yes, you need to somehow aggregate them together. So you can use, if they are all the same type, yes, a sequence is a great way to do that. If they are of different types, there's a tuple in the language. So tuple can be arbitrary size, mixture of types, just like you may have seen in Python. Yeah, that's totally fair game. Great. Okay, so guess what? We have functions, and so we're immediately going to say, what about recursive functions, right? And so let's see how it looks, right? So notice how this function looks a little different than what we saw on the prior page. Number one, yeah, it's multi-line, so we have to have the curly braces. You may also notice we explicitly specified the return type. So this time we say it's and then we say colon return type. So it's the same kind of syntax we saw before, right? Name, colon, type, function, colon, type, right? Okay. This time we had to specify the type because if you have a recursive method, it needs to know the type. That's a rule in the language. If I was to remove this, it's going to yell at me. But I'll leave it on for now. And if I drop it off, let's say recursive function should have a type. Yeah. Okay, so what's going on in the body here? Well, it's a recursive function, right? So we have our base case, and then we have, our inductive recursive step, right? And so here we are just adding up the numbers from n down to 0, right? You can see, okay, we take the current and then say, oh, run the same thing again with rexsum n minus 1. Great. So, 4 plus 3 plus 2 plus 1 plus 0 is 10. Great. Um, if for some reason your function doesn't want to return anything, you can use the name explicitly unit, and that's like void, right? Um, so from your prior programming experiences, when you write a recursive function, what do you need to think about? Number one, what is your base case? How is this going to end? And then you can think about what the recursive step is, and et cetera, right? So a canonical recursive function you've probably seen in other languages is the Fibonacci sequence, right? So our fib function, of course, when we get sufficiently small, we just return n. Otherwise, in the Fibonacci sequence, each sequence element's the last two elements, we can kind of just break it down recursively. And so, yeah, it's a very pretty recursive expression of this function. Algorithmically, it's not the most efficient way to calculate Fibonacci. We know that, but we'll ignore that for now. And yes, here we see that sequence we like because of the for loop we're calling it multiple times. We can say, oh, yes, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, Fibonacci. Yes. Great question. So here I'm showing Scala. How would this look in Verilog? We're going to show that in a few slides. The short answer for now is this is the Scala in the program that's running. The Verilog is, you think of like the residue of the hardware that was generated. So whatever your recursive function builds up, when that code ends, that's what it turns into the Verilog. Question, yeah. A question was, okay, so just using Scala recursion, is that applied to combinational or sequential logic in hardware? Both, right? So like I said, it's kind of this game we're doing here where we're building up hardware. The hardware, when it comes to building it, it's really just a matter of declaring it. I want a adder. We saw a mem. I want a wire and connecting together. So it's really just instantiate component and connect components. Everything else we're doing is actually all Scala rather than Chisel. And it's we're kind of choosing what to instantiate and how to connect them together. And so, yeah, for that Scala code that surrounds these Chisel operations, that can be a straight line code, it can be loops, it can be functions, it can be recursive functions. That's all fair game. And using all those programming constructs, we can kind of build more and more sophisticated and intelligent generators. Cool. And so you may be thinking, why recursion? Well, why recursion is because it's sometimes a really helpful way to think about problems. It also is a way to keep this style of having everything be immutable, all vowels, and yet you still have that iteration ability with like an immutable thing. In terms of runtime overhead or anything, sometimes recursion can be slower if you're not careful, but it doesn't matter because it's going to be in a generator. It runs once, and then the hardware is generated. The hardware is going to be no less efficient, right? Cool. So we were just talking about a second ago, right? How are we using Scala to construct these children components, right? We are just instantiating things, connecting them all together, right? And so the goal is, this is more of a software engineering goal. We want to encapsulate, we want to hide the complexity, right? We want somebody to have a generator and they can just give the parameter generator needs and then use it. They don't want to think about what's going on inside, right? They don't want to worry about that. If we do a good job of choosing what we hide and what we show, they shouldn't need to care what's inside there, right? And so you'll see as you're designing your own components and your own abstractions and your own design, you may want to reuse certain things, right? And so the goal is, how do I declare something once and use it in many places and get great utility and reuse out of it, right? And so one such tool for that is recursion, right? It's a way to perform iteration with parameterization, of course. And so we'll see that. Another thing we're going to see today is, until now, we've been telling you, Yes, every bit of children you declare needs to be in the module. That's only like 90% true. Technically, we can construct things outside of a module, with, like, for example, with functions. However, eventually that component needs to be wrapped into a module before I generate Verilog or before I run a tester. And so we'll see how that goes. So we also construct components outside a module and then pull them into a module and instantiate them, etc. And at the very end, of course, we'll come back to something called bundles, which is how we kind of get some structure to our design. So you may remember from just 2 lectures ago, but it's actually just 2 days ago here in person, we built that shift register, right? We said, hey, I want to have something delayed n cycles. And we did that with a var and a for loop was one way we wrote it, right? And the reason why I like the var for loop one is that one allowed us to have even a possibility of zero delay and then gracefully, changed over. But, if we want 2 cycle delay, sure, you got it. So that was what we did before. Now let's try this recursively. So we're going to have a helper function. This is often the kind of way you set these recursive situations where you kind of have your recursive function and you declare it as a nested function in this case. And then you're going to wire it up like this, right? So, okay, so base case, no more delay. I just pass out the last section I've been given. If I have n, not equal to 0, well, then I should call myself again, but then using recursion, take the output of this thing and wrap it inside a reg next and go on there. And so this is going to produce basically the same code. The naming is a little different, but structurally it's the same, right? And yeah, this also has a nice property to be able to handle 0 or, arbitrary depth, whatever. Um, so comparing these two side by side, I guess the one on the right has the virtue of having no mutation. Mutation's kind of handled by effectively creating these new method contexts every time it does the recursion. So there's no var. Both of them have the same external functionality. Both of them have the ability to give a user an n cycle delay, and n can be 0 or greater. So both, check off a lot of boxes. I think some people probably prefer the one on the left. They might find the idea of mutation in a for loop with a var more clear. For this course, if you're trying things out, I would suggest try the thing on the right. It may not look simpler and it may not be simpler, but it's kind of good to experiment and see what happens. And I think for the sake of building up your own design style and your own coding style, it's good to kind of push yourself a little bit and see what kind of makes sense. And you may find for some more sophisticated problems, the recursive one does look a lot cleaner than the mutation one with a for loop and a var. Cool. Questions? Let's go ahead and now talk about Scala objects. So the naming here isn't ideal. So you've heard me talk about class and object and keep talking about objects. Uh, let's kind of be clear about what's what. So in object-oriented programming, an object, is some instance of something, and you can have methods, you can have fields to it, etc. Of objects, there's kind of two styles, right? There's objects where you can have arbitrary number of instances, and there's something called a singleton object, meaning that no matter what, there is exactly one copy, right? There's never 0, there's never 5, there's always 1. That object exists as soon as the program exists, and as soon as the program dies, that thing ends. And so that's called a singleton object. And so in Scala, that's distinguished with the object keyword. So here we have a class called myPair. So you can have an instance of myPair. Then there's object myPair, which is a singleton. So there's only one singleton myPair. And then I can have instances of the class myPair, an arbitrary number of instances, right? 0 to, n. Having a singleton object and a class with the same name is a very common design pattern. And this predates Scala. It goes back to object-oriented languages. This is often referred to as the factory pattern or factory method, right? And the fact these two have the same name, this is what's called a companion object technically, right? But basically, the way it's set up is that someone can use this object to instantiate the other one. So this kind of how this plays out. So if I declare a class by itself, let's say making a class for a pair, sure, it takes in A and B as two ints. It has those fields, and someone can call sum on it to get the sum of those two things together. So if I was to run this code, sure, I can declare, new instance of a class is new and then my pair. I can add them up. One interesting thing about Scala, if you have parentheses on something as a function invocation, and there's no argument, it's a blank parentheses, um, you can actually omit them. So notice how NPC sum without parentheses. That works just fine. Stylistically, this is encouraged when the function returns something and does not modify the class instance. If there's any kind of mutation involved, this is strongly discouraged, right? Because if someone reading this code, this syntax is indistinguishable from me calling a function or just some being a field of the class instance, right? And guess what? If it's an immutable function doesn't change anything, the fact that it's a function call versus a field maybe shouldn't matter to someone on the outside. That's why they chose to have this possibility. But if you're mutating things, you should use the parens so that way it's clear what you're doing. But if you're reading someone else's code, you see that they seem to have somehow omit them. That's why. Cool. So let's see how they use this singleton object in a few ways. Um, so we can do a few things. We can, number one, let's say we want to track how many pairs have ever been instantiated. This is a way to kind of do that. Rather than having somebody every time to call new my pair, needing to increment some sort of counter or something, I can, at the time this is done, intercept that call. So um, what is this code right here? Calling this on the object name, which happens to be the same as the class name, but the compiler is not confused. And then giving these arguments, what's it going to do? Well, a apply method in Scala is a special keyword. And so apply is going to kind of elide the apply and basically do this, right? So you're calling this function. And what does that do? Well, it adds one to total number of pairs and it returns a class instance. So from the point of view of the user, they called my pair to 3 and they got a my pair object, right? This object we're returning, if I was to do this actually returns a second my pair. I can call sum on it, sure. Now if I ask it how many my pairs has been made, oops, I gotta uncomment that. It's gonna tell me 2, right? And the reason why is counting these two calls. These two calls use supply methods, so they're going to be incrementing this num pairs. These other instantiations kind of bypass this object, right? They go directly to the class itself, and that's why they're not included there. But you can see using this kind of factory method, we're able to interface yourself into this. So you may have thought looking at this class primer from last week, where you have this argument list, it was kind of very cumbersome because sometimes for a class, you might want to have different types of constructor lists. Maybe you want to have, simpler constructor lists or longer constructor lists. And in this case, we only had one for the class, and this probably seemed very constricting. The answer is you can actually have that flexibility by using these factory methods as apply methods on the companion object, right? So I can have a constructor of 2 arguments. I can have a constructor with 1 argument, which under the hood just calls the 2-argument constructor apply, and it gets 0 for the second argument. What's nice about that is that notice how this is coded up, right? By calling the other apply method, numpair is also incremented correctly, right? It's all kind of tracked. But having a single source of truth, right? This all comes together. So you've been using these singleton objects and not known it. For example, when I say something like, seek 1, 2, 3, right? That's an apply method on the seek object that returns a seek instance, right? So you may be wondering, why are we covering this in this class? No pun intended. We use it a few times, right? Much of the time we're using this class construct. There will be times when we want to use the singleton object, right? Sometimes we want to have these factory methods to handle different cases for us. Sometimes we want to keep track of our class instances. Sometimes you may just want to have, in not notebook land, but actual proper Scala land, you just want to have a bunch of Methods, right? Methods need to live in either a class or an object. If there's no per instance state that makes sense, sometimes putting them in an object makes more sense, right? Because otherwise people have to kind of instantiate an object in order to use it. And instead they can just go directly. So you'll see it in all these kind of cases. So yeah, class and object, both are in object-oriented features. Class is a, you know, instantiable type of class versus object is a singleton. Whew, okay. Questions? Yes. Which one? Up here? So within here, yes, this new command is instantiating an instance of this class. So they happen to have the same name. That's actually not a requirement. I could make this my pair two, and that would be okay. And this will also be my pair two down here. Um, however, uh, you can have these two have the same name, and it's referred to as a companion object, and then the compiler can figure out which one you mean when you do to certain things. But yeah, so basically we're using the singleton object to produce instances of this class, right? And so that's referred to as a factory pattern in object-oriented programming. Um, this is one way to kind of doing objects. So rather than having objects that have their own internal constructors, you have another bit of code that understands how to build that object and handles that for you. Other questions? Okay, let's use that factor method we were just talking about, right? And actually put it to work in Chisel. So you may remember from a couple lectures ago, we wrote up our code for our counter, right? So that's this class above, so we have class my counter, there's a maximum value. I told you this is boilerplate, but now you kind of understand more about what's going on. This is object-oriented inheritance from module, which is a chisel construct, and that kind of makes it chisel appropriate. We have our, input, a single Boolean wire if true. We're going to enable to increment every cycle. The current counts an output. Here's the code from a couple lectures ago where we, have register set to 0. There's some additional work here to kind of figure out the right bit width. And then, yeah, if counts true and it counts below the max, just add 1. If we are equal to the max, then we swap around to 0 and wire it all up. So we did all that. So I can go ahead and declare that method and write the Verilog, and we've seen that. If I use the factory method style, so in other words, I have an object also called myCounter and supply, and that just returns new myCounter. Yeah, that's going to work just fine and should produce literally the same Verilog, right? So this is all in Scala land. It's indistinguishable in Chisel land. But you'll see in certain cases, having these factory methods allows you to better encapsulate your Chisel for these generators, where, like I said, it's very common with generators. You want to have not just parameters, but different combinations of parameters and have that, diversity of constructors. You can do that by having multiple apply methods inside of your companion object much easier than you can with just the class by itself. This is a trivial example and doesn't quite show the full power, but it shows it at least functionally. We'll get more examples in a second. Question. So the factory method allows us to kind of, the question is what's the advantage of this factory method? The advantage of the factory method is you can now have the intelligence and logic involved with creating an instance separated from that instance itself, right? So in a lot of languages you may have written before, you would, like C++, you might have multiple different constructors. Okay, constructor A, constructor B, constructor C, and you put that inside the instance, right? By pulling it out, it's the same code, right? It's not like we're magically eliminating code, but it can be more clean, right? The instance can focus on doing what the instance action needs to do. And this companion object then has the smarts about how to construct it. For us, pragmatically, as hardware people who don't care about software, we just care about making nice hardware. What we care about is the ability to have multiple constructors, right? With the class syntax in Scala, you only can say, new my counter, and that's it. But if I want to have the ability to have different types of parameters, I want to have, constructor A versus constructor B versus constructor C, by having different apply methods in the companion object in this factory pattern, I can do that. Yeah, good question. So could we use the term overloading to describe my counter because it both refers to a class and an object? I'm not quite sure overload is the right term, but you're right, it's the same name. The compiler, based on the context, knows what you mean, and the fact they have the same name binds them together in some ways when to call a companion object. Not necessarily. I could make this, like that, right? And then it would need to be this. I think that should also work. Oops, I gotta run that code. Yeah, that's fine. So they're required to be the same, but they can be the same. That's a lot more clear to people reading it what's going on. You'll see in a second, I'm going to show you some examples from the Chisel Standard Library. In the Chisel Standard Library, sometimes they have to be the same name. It's very clear where it comes from. And other times, it's not the same name because the thing it's using is actually named for some other reason and it's kind of hiding that name. Um, so let's see a few different variants of this. How about if we want to do our module, or sorry, do our counter, but we want to do it outside of a module, right? So in other words, this is a Scala class. It, takes in a maximum value that is a Scala int, takes in a chisel wire enable, which is a bool, and it has kind of that core logic for our counter. And then if somebody wants to instantiate this, they can use the companion object to go ahead and say, hey, I have a maximum value in that enable. It's going to go ahead and call that function. It's just wired in there, and uh, we need that output. So then it's going to go ahead and return the output as the result of the supply function. So technically, what does this my counter apply return? It returns the count, which is a register that was generated by this function. Now, the register is not alone. There's a lot of stuff surrounding it, but that counts the result of all of that. As I said before, it's perfectly fine for us to declare a chisel like this, but before I can turn it into a Verilog or before I can simulate it, it needs to find its way inside of a module. So at the very end, I'm now instantiating a module later on, and I'm instantiating this. You can see that actually syntax is perhaps more simple than you might expect, right? I'm just saying, hey, my counter, this my counter, it's not new my counter. New my counter would be up here. My counter directly is calling in the object. The object with the parentheses right away, that's the apply method. So it's the supply method. This is returning, mc.count and second to this count. So at the end of the day, we get the same Verilog coming out the other end. Um, this example is, you know, putting it all these different features together. This is probably not a more clear way to write a counter, but we're showing these features kind of in the most concise example I can show you. And we'll see as the quarter goes on, more sophisticated usages that actually justify usage of these features. Cool. Okay. Yes. Are there other object-oriented design patterns besides factory and singleton? Yes, they are not on tip of my tongue at this moment, but definitely, right? They are definitely both possible in Scala in general because it's a very flexible language, but also there are some Scala even encourages. Forgive me for not remembering right now on the spot, but I'm sure there's other patterns for sure. Okay, so we've written counters so many different ways, and it's like a really useful thing. So is it in Chisel? Yes, it's already in Chisel. It's already in the standard library. So let's take a look at that. If we go to the Scala doc page on it, so yes, it's part of Chisel util. There's a counter, and you may notice how counter is why I use this for these examples. Even here in some examples right here, there's actually multiple different variants, right? There is a counter which has a count enable and a maximum value. There is also a counter which takes in a range, and it does that. Um, so you can see our array is kind of some cleverness about what we're doing. You may also see that here we're taking the wires directly out of the counter. Uh, this is not returning a module, right? Um, So you may see this kind of notion of whether something is or is not inside of a module. As we're building more sophisticated constructs and hardware, you may find it easier to have some pieces not always be modules, right? And so what's the trade-off between putting something in a module versus putting something in a function? The advantage of putting something in a function, especially for a small bit of hardware, you don't need to worry about having these I/O ports because you can just have the fields coming in as arguments, right? Meanwhile, the outputs, you can have a couple outputs just fine. So that's the advantage for having things as a function, not in a module. Is yeah, you can very quickly do things. You can avoid needing the IOs. The other reason why to avoid modules sometimes is if you have tons and tons of pieces going together, the emitted Verilog, every time you say module and chisel, you get a module and Verilog. And so the emitted Verilog has a bunch of Verilog nestings and stuff like that. And depending on the CAD tools you're using and how you have them configured, module boundaries can be significant, right? Some CAD tools will or will not, under certain circumstances, optimize across module boundaries, right? It kind of treats the module as a contained unit, and it won't go inside there. And so sometimes for your design, really the module is kind of this bigger thing, and the fact that all these internal pieces were stitched together from different Scala functions and classes, great. You stitch them all together. When you have the thing come at the other end, you might be happier of having that as a single module rather than having a module with a lot of nested modules inside of it. That's a design choice, but there are some reasons why, except with some CAD tools, some of the time this comes up. Our own group's had to deal with this recently, where some organizations we want to do on FPGA CAD tools do not go across module boundaries despite the flags we give it, and so we've had to take some of the module keywords out of our code to have more of a kind of chisel, Scala, native Scala construction to avoid that issue. Okay, let's see the chisel string library counter in action. So we're wrapping in the module. We have an input to enable it, the current count, and we also have this notion of limit. In other words, letting us know, is it reaching the limit? So sure. Notice how counter actually returns two things. So earlier in the lecture, we were talking about tuples. This is an example of a tuple. It's like anonymous, right? It's just, two things joined together by parentheses and a comma. These are two different things coming out of the counter, and we can attach those to the ports. And so this works just fine. If I generate the Verilog, sure, it all comes together. So you see, for example, the count is what we expect, the value. What is this wrap? This wrap isn't just that the value is the maximum amount. It's the fact that you're going to wrap around, in the sense that you're at the maximum amount and the count enable is high. So as a result, you're going to go from that current max value to zero. So it's telling you you're wrapping. So that's why you can see in the Verilog code, for example, is that wrap, the limit is both, enable and wrap, right? Cool. So here we are instantiating it, the wires. You could also, of course, instantiate a counter with a, sorry, go ahead, you have a question? Oh, no. You, of course, instantiate it with a range. And what's interesting about this one, for example, you notice how the range goes by two. So our counter is going to add two every time. Sure. And this is kind of a pretty cool bit of stuff, right? You can imagine where this is very, Scala-y to have this range come in, and then this is somehow being turned into hardware. Cool. So I'm going to we're going to pull back the code on counter in a second. Until then, any questions first? So let's go look at how to implement this. So here we are in a Scala doc. And how is this actually built? So we see there is a class called counter. And it has things like the range, in this case, the range syntax, as well as, uh, things like the old end value. Okay, but see inside there is all this stuff, right? Where there's a lot of complexity. There's some, stuff here for handling legacy versions of the counter. But the reality is that actually you as a user are going to be calling the object counter, right? And one is apply methods, right? If I just want a simple counter that counts up to, n, yeah, you get a new counter n, right? If I have this, condition, guess what? It's going to use the condition to control whether a counter is incrementing or not, right? So we're still instantiating a counter, And then there's the increment method. If I want to do a range, it is doing that as well. So how does it use this range? Uh, it is calling counter on the range. So going back to counter, you can see counter both has the ability to handle a range as well as an integer. So how does that work? Let's go back to counter. And here we are kind of handicapped by a browser rather than an IDE. But yeah, you can see that for the old option, it can do the int, but there's also the range option. For incrementing, there's some math stuff here. We've not covered all the Scala yet. Most of the point of showing this example is to show that there's a object which has different constructors, we apply methods, and that turns into creating the class counter for us. And so, like you've seen in many classes in undergrad, remember your data structure algorithms course where you build your own data structures and they tell you use a standard library. Same thing here, right? We've built our own counters. You've done it in assignments already, and I'm telling you when you actually use it in your designs, use a standard library, right? When you use a standard library component rather than running your own, that's not just less code writing, less chance for error, right? If this is a standard library component, hopefully it's been widely used and widely tested. More likely to write whatever you write yourself. And you might say, oh, well, maybe mine's more efficient. It could be, but maybe theirs is more efficient because they've had more reason to optimize it, right? And so, in breaking the Agile philosophy, you might as well at least use standard library objects when you can. And then in a situation where you think yours might need to be written yourself to be faster, have the measurement to know you actually need that and you actually make it go faster first. Cool. Yes. Oh, good questions. If I use these chisel library components, can I get in trouble when they deprecate or remove things? Their deprecation rate's been pretty slow. They have deprecated a few features over the years, but they were fortunately extremely rarely used. And so yeah, I would definitely encourage the use of standard library components. They've also had various compatibility layers over the years to kind of support prior versions. So for example, we're using Chisel 361 in this course. The Chisel 3 series lived perhaps maybe almost 8 or 10 years. That was kind of a long used version number. But even in that time span, they actually supported Chisel 2 for quite some amount of time. And Chisel 2 was actually literally a different code base. And they had a pretty good Chisel 2 compatibility layer that was available, not in Chisel 3.6, but before then it was still available, maybe in 3.4 or something. And so, yeah, they've had a pretty good track record of having backwards code compatibility. And yes, in this course, we've heard bemoan the loss of Chisel testers and the new versions of Chisel. That was one of their more, stark departures. But in general, yeah, use standard library whenever possible. And hopefully they won't pull the rug out from under you. And usually they don't. Okay. And then wrapping this up, let's add some more structure to something called a bundle. So a bundle, I like to think of these like a struct in C. I can have named fields in something, right? So in other words, I can have something, I can put fields in it, and have, each of those have names. And so we've been seeing bundles so far and not even knowing what they were, because if I go back a slide or two, this keyword kind of lurking in here, and we're using it to make IO. You can use it for a lot of things, right? So you can make a bundle. In this case, we do that by extend bundle. And yeah, let's go ahead and toss in a 4-bit field called M inside mag. And then if I want to instantiate a module, instantiate that bundle, I can just say, new mag. New mag is a class, of course. Sure, I can go ahead and instantiate that. It's an IO, and then um, I can reach into a field of it with the dot operator, no problem. And of course, I can connect it to something else. In this case, I'm taking a Scala int and turning it into a chisel u int, right? So after all that hoopla, this module just, produces um, literal two. If this clock and reset really bothers you, there is a way to make that go away. Um, that has no advantage in the hardware. Having that clock and reset there that are not used costs you nothing. The CAD tool will prune that away automatically. But like I said, if you're really curious to not have that, yeah, raw module can do that. And yeah, as you can see, yes, it's just a single output. But I figure the best practice, just always use module and it'll always do the right thing. Cool. So we have a bundle. we're going to see how to go ahead and use that, right? So what's cool about bundles is we can compose and build them up. We can nest them. We can extend them. So let's say, for example, I want to do number representation. How about a sign and magnitude style number? So I could take my magnitude, which is the first bundle we made, M. I can make a sign and magnitude, which extends mag. So even though I can't see it, this has the field M from mag as well as this new field S, which is a bool, which is a sign. I can also instantiate nested, right? I can say, hey, I want to have a pair of sign and magnitude numbers. And I could have had num0, num1. In this case, I chose to make a vec. So these are not just fields, you can actually have some amount of smarts in here, right? And so let's say, for example, I want to make a module that has two sign and magnitude numbers in the midst, always constant literals. And how can I instantiate all that? Sure, I can go ahead and instantiate as IO this bundle type, and I can go ahead and wire all the stuff up. And so notice how, what do I have? I have, even though I instantiated just pair sign mag, pair sign mag has nums. There's two elements because it's a vec. So you see nums0, nums1. Each of those elements is a sign mag, which a sign mag has the field S, as well as everything that was inside of mag because it extends that in the object-oriented inheritance sense, right? So, um, cool. So it's kind of a long way to generate a bunch of literals, but we'll see some applications of this in just a second. So yeah, so you can put bundles inside of Vex, you can put Vex inside of bundles, you can do a lot of cool stuff. And so you see bundles is really great way to kind of start building some structure. So if you're seeing bundles, you see old chisel code, you might see something called clone type, where you can see when you wanted to write your own bundle, you had to write this override def clone type, blah, 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 blah. That was really ugly. Guess what? The Chisel compiler folks got really, really clever, and Chisel 3.5, which is now a couple years ago, removed the need for that. This is not necessary. So you don't need to worry about this at all. Why do I include this slide in the lecture? Because I want you to be aware of the fact that this language is constantly evolving and improving, right? So this is something that was annoying. They fixed it. That was great. Cool. Now, bundles are just kind of the starting point, right? We can start building on them. So we can have our sign and magnitude bundle. Sure. In this case, we chose to do it redefined all at once. Now, what's kind of cool is let's say I have a module that's going to have an input bundle and an output bundle. I could write it like this, which is going to simply connect, the input field for both fields separately. Or I can use this spiffy operator in Chisel called a bolt connect operator, and it's going to connect bundle on bundle. So I can just have one line connect these bundles entirely. And what may not be obvious right now, this is an extremely clever operation. It isn't just a matter of connecting all the fields. You actually can have situations in which the bundles on both sides aren't exactly the same type, and it's pretty smart about how it figures out how to handle that. There's a lot of operators for those connections. So if you have really complicated designs, really complicated bundles, you may want to consider all sorts of different ways of handling these interactions. We don't worry about them in this course because our designs don't really get that big. But for those of you who are aces, this is extremely important and extremely productive, right? Think about it. When you're writing hardware designs, especially in Verilog or Chisel, very quickly a large fraction of your line count is I/O, right? It's like inputs, outputs, inputs, outputs, inputs, outputs. And you not only declare the inputs and outputs, then you got to connect them all up together. So having these abilities to these bulk connections, especially cleverness in bulk connections in terms of how you do it in various ways, that's a really helpful feature. So some of these super sophisticated operators are only available in the more recent versions of the Chisel, not available in version 3.6. But I just want you to be aware they exist. Um, this bulk connection, the classic one, we will use, right? Because it makes life a lot easier. Also understand that when you have these two bundles, right, the directions, right, in terms of inputs and outputs may be different or something. It'll do the right thing and figure things out in that sense. And if it can't, it'll tell you at compile time, which is helpful. Cool. Questions? Yeah, so this said a second ago, you can have bundles that have wires in both directions. So your bundles can have, on this slide, the fields have no direction. It's just a uint or a bool. Or I can put a direction on them. I can say, hey, this is an input, this is an output. And so if I instantiate handshake, ready is an input and data is an output. If I call flipped on handshake, as your name suggests, it is going to be the opposite of directions, right? So now ready is going to be an output and data is going to be an input. And so you can see with declaring directions, there's kind of a few options available to you. On this slide, the bundle had no directions, and we kind of globally applied it to the bundle, and they all got sent the same direction. But oftentimes, the more sophisticated interfaces, you're going to have bundles where that bundle will contain things in both directions, and so the directions are kind of baked into the bundle, and maybe different directions, and then you can still do things like flip to kind of work with them. Cool. And then this keyword you saw 10 minutes ago, didn't know what it is. Now we're finally going to cover it. Before I do that, I'm going to ask if you have any last questions on bundles. Okay, so what is this option type? This is something that's pretty cool about Scala. It's a way to wrap around something, and so whatever type you give it, you can either have this is that type or a none, right? In other words, it doesn't exist. And so this is really helpful. Sometimes you want something and you want to know it's there versus not there. So in really risky C code, you may see the notion of, oh, if a pointer address zero, well, pointers can never be zero. So if it's zero, i.e. null, that means it's empty, right? This is like that, but way safer and better, right? So there's a variety of ways interactive options in Scala. For today, we're going to use is defined, meaning true or false. Is defined if it's a sum, meaning it exists, you get told true. If you call is defined on something that's none, it's going to tell you false. And you're going to call a dot get, which will give us the actual thing inside there, if it exists. If it doesn't exist and you call dot get, you're going to cause a problem. So why are we doing all this? In a minute, we're going to show you how to use option to have an optional field in your bundle. But first, let's put Scala first. So let's say I have an option O that is type int, and I say sum4. So good. I go ahead and this code here I call is defined, and if it is, since it is defined as a sum, it goes ahead and grabs the value, right? 4, prints it. If I alternatively had a none here, it'll be not defined and it's going to print empty. Sure. What if I didn't check and I just try to grab it and it's none? We get an exception, right? I call get on a none. Like I said, so you're going to avoid that, right? You're going to check first. Now, the checking seems like a lot of work, right? But we'll learn more elegant ways in Scala to more gracefully include that checking logic. But yeah, it's just a way to kind of note something either does or does not fully exist. So let's see that in the bundle. So now I can have an optional IO. In other words, an optional port. So I have this maybe pair. It always has the field X in the output direction. Now with this Scala Boolean, I can say if there is or is not going to be another field. So this Y is going to be an option type. Children understand what that means. And so yeah, if someone wants the Y field, they say has Y, sure, I add this Y field. If this is false, this is going to be a none. And so yeah, if I go ahead and look at this module, what do? Well, inside this module, I use this, bundle I declared, sure. Takes into Boolean to kind of control this use Y. So yeah, if there is a Y, I go ahead and grab the Y and wire it up and connect it. However, if I turn this whole thing off, it goes away, right? No ports, no hardware associated with it. This has become a very powerful way to not just, you've already seen in last week, you can use the Scala if statement to have hardware that does or does not exist based on the parameter. In this case, we're now using that to go not just inside the module, but actually the module boundary to have an optional port. And so a option is one way of doing that. The other way, of course, is using like a vec and having like a zero element vec. I think an option makes more sense if it's either 0 or 1. If it's 0 to n, then a vec makes more sense conceptually. Cool. Questions? Okay, so then as one last little wrinkle, um, we saw earlier in the lecture we had like populating a seq with a var. There's a helpful built-in function in Scala called tabulate, which allows you to kind of do a fill but rather than just filling everything constant, in this case, just fills, a four-element seq with all zeros, it's going to call a function every time it's called, right? And so we covered functions earlier. This is a different kind of function. This is an anonymous function. It's a really short, concise syntax. Um, so in this case, it takes in an input I and the function returns I. Or you can even have a more aggressive syntax, what's called placeholder syntax, where it returns this and this underscore is the first argument. And you're only going to use that once. And so you can see, okay, sure. I call seek.fill, I get four zeros. I call tabulate where I give it an input, I just, return the same thing. Yes, you can see tabulate is going to call 0, 1, 2, 3, which is less than 4, and that's what you get. If you use this placeholder syntax, it's really concise, kind of clear. You can do some more clever things. Um, Sometimes you back yourself into a corner. If it happens, don't use the wildcard. Instead, use the more natural function definition. Cool. So like I said, this is the way to kind of build things up. And so we're going to go ahead and use that in the labs and homeworks this coming week. Cool. Any questions on that? Okay, well then to kind of wrap up. So we covered a ton of features. So I think this is good to kind of take your time with the labs, take your time with the homework to kind of make sure you're getting a chance to play around with them. There's this balance in this course where we try to make these simple possible examples to show just the feature in isolation, but sometimes it's so simple that the motivation may not be obvious, right? But they get useful when you kind of get larger designs and more meat to them. And so it's good to think about, okay, how do I make these things to make my code better in some way? And what is better? Well, Scala helps you a lot for safety, which is great. I also, when I say safety here, I'm referring to like how correct is your design? Like, can I make my code in a way where like I know I can make mistakes writing the generator, or someone's making a mistake using the generator? How can I make that safer, right? Um, how can I make my generator more productive? Right? How can I write fewer lines of code to get more functionality, kind of a more graceful, nicer way? Or how about just easier to read, right? Between these complicated features, is there a way to kind of balance and make this actually more clear? And kind of the key thing when it comes to complexity is thinking about encapsulation. That is, there's going to be complexity somewhere. How can I best put it only where it needs to be and not where it doesn't need to be? In other words, pull complexity down to where it has to be and hide it otherwise, right? We cover things like methods, which is a great way to kind of group things up and how to build up hardware components with methods and objects without even using modules necessarily. And as you can see, we're getting this kind of more programmatic way to build hardware. We aren't just saying a single line is a single piece of hardware. We're making programs that assemble hardware, and that's pretty cool. We saw factor methods of companion objects, and we also saw bundles. You're going to use so many bundles. It's a really helpful feature, and it's good to have that flexibility in them. Cool. Any last questions? Okay.